So our previous problem here, sample problem 8.6, talked about writing electron configurations for main group ions. And in this case, our last one here, it really wasn't really a transition metal because indium didn't really fall in the transition metal category, but it still had a situation where we had multiple oxidation states that we considered for that ion. So this problem becomes a little bit simpler because these are specifically transition metals, but they do tell us which cation we want to form. But we're going to treat the problem the same way we did the other problem. We're going to write an equation to show the formation of the ion, and then importantly, in this case, it asks us to say whether or not it's paramagnetic. And another way to ask if something is paramagnetic is ask, are there unpaired electrons? So are there unpaired electrons? If the answer is yes, then we say it's paramagnetic. All right, so a little bit more quickly through this problem since we already dealt with problems like this in our previous one. So we can write the electron configuration for the atomic manganese by taking the previous noble gas, right? So if we're looking at manganese here, the previous noble gas is going to be argon. Then we're going to have 4s2, 1, 2, 3, 4, 5, 5d5. So 4s2, 5d5. It tells us that we want to form the manganese 2+ cation. So hopefully there's logic to removing those 2s electrons in the 4s orbital. So again, that gets us to be argon 3d5 plus 2 electrons. Now, this problem doesn't ask us to write orbital diagrams, but I like having orbital diagrams because they help me think about the paired versus unpaired. So again, if I take and I write an orbital diagram just for my 3D orbitals, and there's 5 of them, and I have 5 electrons to put in there. Hund's rule is again going to have me add the electrons in this way, and I can see that all electrons are unpaired. And even if we had just one electron that was unpaired, that would tell us that this species is paramagnetic. Okay, next example. Chromium 3+. So again, as we keep working through these problems, each time we do another flavor, see how it's different from the one that we just did. All right, so here quickly we're going to see how this one's different. If we look up chromium, again chromium being just one adjacent to manganese here, it's going to have argon as its previous noble gas for our condensed electron configuration. And then you'd think we'd go 4s2, 5d4. But here's what we're going to see here. Chromium is going to be one of these funky ones like copper that likes to behave a little bit differently, and see if the logic to this makes sense. We're not going to have 4s2. Maybe I'll write this down and then cross it out. We're not going to have 4s2 and then 3d4. That's not what we're going to see here. Rather, what we do see is 4s1, 3d5. And the idea here is that we are better off having a half-filled d orbital. So it's going to look kind of like this, where that 3d orbital has an electron in every box. Whereas if we took one of those electrons and put it in the 4s orbital and had 2 of them filling that, then we would have a less than half full d orbital. And once we get into filling these kind of higher level seats and our best, fill the best seats first kind of analogy, it's actually going to be best to fill things in this way. So this is going to be the correct electron configuration for chromium in its atomic state. It tells us we want to make the chromium 3+ ion. So chromium in the 3+ means we're going to actually remove that 1s electron as well as 2 of the d electrons. So chromium's electron configuration as the 3+ ion is going to be argon, and then 3d3. So again, removing this 1s electron and 2 of these d electrons. Again, writing this as an equation. We've removed 3 electrons. It's probably easy just to see here, but to draw it out to be consistent, in our partial orbital diagram here, just showing the valence electrons here that we have remaining. The 4s orbital is now completely empty, but the 3d orbital is going to have 3 electrons in it. All 3 of those electrons are unpaired. So again, this is another paramagnetic species. All right, last one here is Mercury in its 2+ state. So Mercury kind of puts us way down in the periodic table here, atomic number 80. Our previous noble gas is xenon. So again, if we start with just the electron configuration of our starting atom, it's going to be xenon. And then moving forward from xenon, we're going to have 6s2. This 4f orbital is going to be completely filled. Then we're going to have the 5d orbital is completely filled. And again, that gets us exactly to the end here with Mercury. So 6x2, 4f14, 5d10. So when we take this guy and we're going to remove 2 electrons to make the Mercury 2+ cation, makes sense hopefully that we're going to remove the 2 electrons from there, as that leaves the other 2 F and D subshells completely filled. So again, we're going to lose these 6s electrons, so we're going to be left with 4f14, 5d10 as the remaining electrons. So we've lost those 2 electrons. And again, here we're completely filled. And when electron orbitals are completely filled, that also means that we are completely paired. Okay, so there is nothing unpaired. So we can use another term that your book really doesn't use, but we can say that this is